Hello friends and welcome to edupediaworld.com, your destination to online education. Friends, today we are going to study absolute zero and we'll be discussing ideal gas equations. But before this, let's rewind what we have understood all these gas laws. We learned Boyle's law, Charles' law and pressure law. We also call it Gay-Lussac law. These are the standard variables, that is pressure, volume and temperature, in which the gas depends. We also learn all these combined gas law, that is we also learn gas equations, Boyle's law with the Charles law and pressure law. We can see out here Boyle's law is volume and pressure relation. In Charles law we learn volume and temperature relation. In pressure law we learn pressure and temperature. Keeping all these combined, we learn PV upon T is a constant, that is P1 V1 upon T1 is equal to P2 V2 upon T2, which is will be very important uh, formulas for the numericals. Now, in this session, we are with absolute zero and we'll be learning bit of ideal gas equations, that is ideal gas law. But before starting, let's take an example and understand what is absolute zero. Okay, take an example. This is a mountain, right? This is the highest peak of the mountain, and there is a mountaineer. There are many mountaineers. This is Ram. This is Raghu. This is Sunil. This is etc. Some Ram have reached here, Raghu have reached here, Sunil have reached here, but nobody, no mountaineer has not reached here. That is the highest peak, right? Or we can also take an example like this is the sea water and this is the deepest layer of the sea. Let's suppose there are two divers. One have reached here, this one, and one have reached this level only. But nobody have reached this level. So what is the conclusion? Everything, every substance, you can say substance or nature, environment, have a highest point or the lowest point, right? So let's talk about the absolute zero. Zero means nothing, that is null, or what we call as absolute zero, that is the highest of, or you can say lowest of null. Let's understand with the example with the chemistry section. See, we know that the air molecules are into the constant motion. This is the air molecule packed in a container. They are in constant motion depending upon the temperature, volume and pressure, right? Now what is absolute zero? See, if we talk about kinetic theory, it says gases consist of very tiny particles, right, which are in constant, or you can say continuous motion, and colliding with each other, and the contain walls of the container in which they are in. Secondly, the kinetic energy increases, that is, the average kinetic energy of the particle increases as temperature of the gas increases, right? That is, kinetic energy is directly proportional to temperature, we can say that, right? So where comes absolute zero? We know that particles get more and more energy as temperature increases and decreases as temperature decreases. So there is a temperature where there is no motion of particles, right? That temperature we call it absolute zero. Now, how do we define? We define absolute zero as the temperature at which the motion of the particles completely cease, right? Secondly, we also know that absolute zero is nothing but the Kelvin temperature scale. If you look at it, starts from zero, right? So if we draw a graph, let's get the section. If we draw a graph against kinetic energy and temperature, it goes straight line. As I had told you that kinetic energy is proportional to temperature, right? So now if we see absolute zero, that is, if we see the scales, what scales we have? We have Celsius scale, we have Kelvin scale. What is Celsius scale? Is if we convert 273, let's take like this. It is minus with the absolute zero. Or take an example of temperature of water. What happens? Let's make a grid like this. This is a Celsius, this is a Kelvin. Let's take this is an absolute zero temperature. This is when the water freezes out. And this is when the water boils. Right? So what happens when the water freezes at 0 and boils at 100? So what is the corresponding temperature in Kelvin scale? That is 273 and here is 373. Now here the Kelvin scale starts with 0, that is absolute 0, and here it's minus 273 degrees centigrade. With this example you can understand what is the relation. The relation comes out to be Kelvin is equal to 273 times of Celsius. This is a very important relation. You have to understand and remember this. Important in all the numericals regarding this absolute temperature. So finally we conclude that the energy of the particles depending upon the temperature, and at zero absolute zero temperature the kinetic energy also goes zero. But we know that most of gases there is a linear relationship between temperature and pressure also, and the gas contract indefinitely as the temperature is decreased. As we theoretically say that at absolute zero where an ideal gas would be zero. Why? And actually in real life all the gases condense to either solid or liquid. Well, above this point, although absolute zero cannot be reached by any of the gases till now, as within a few billionth of a degree above this absolute zero have been achieved in only laboratories. It's not been seen in naturally. So what we conclude is it is a temperature at which thermodynamics system has the lowest energy. Which energy we're talking about? We are talking about kinetic energy. Right? We also conclude that in Celsius the lowest is minus 273 degree. What is the relation between Kelvin and Celsius is this, right? What is absolute zero? Is a Kelvin scale, that is starts from zero. We also understand that at absolute zero only ideal gases reach, although in reality gases either convert to solid or into liquid but have not reached till this temperature. So friends, let's sum up with the definitions and point to be remembered. That is, the 0 point of the ideal gas temperature scale denotes by 0 degree on the Kelvin and ranking temperature scale. This temperature is called absolute zero. Secondly, this is the lowest temperature that can be ever be reached. At this temperature, all the molecular motion ceases. This temperature is impossible to attain. All the gases liquefy or solidify before this reaching this temperature. Now let's see the scales. We have three: Fahrenheit, Celsius and Kelvin. At 100 degree, we boil things. These are the corresponding temperatures. At 0, it freezes out like this. Below this, the dry ice goes freeze, and at absolute temperature, then no other gas have been reached by this temperature. That is, the Kelvin temperature starts with 0, and Celsius is minus 273.15 degrees centigrade, and correspondingly Fahrenheit scale is minus 459.67 degrees Fahrenheit. If you see graphically, let's say A, B, C are three gases, and we plot a graph between pressure and temperature. So where the absolute zero lies, it lies in minus 273.15 till 100. If we see till this point, all the three gases ceases here, but have not reached till the absolute zero. Now friends, let's see the relation. That is, what is Kelvin scale? Kelvin scale is a scale where we see that the absolute temperature starts with 0 and rises up with the corresponding temperatures. That is the temperature scale with 0 at minus 273 degrees centigrade, and whose each degree is equal to 1 degree of this Celsius scale. This is called Kelvin scale, or the absolute scale of temperature, and this relation has to be kept in mind. And yes, the other relation is 0 Kelvin is absolute zero. Now let's keep in mind all these points. That is, no degree sign is written for the absolute temperature value. The temperature on the absolute scale is indicated by capital T, and another scale can be written by small t. The real advantage of Kelvin scale is that it makes the application and use of the gas law simple. And the most important, that absolute zero temperature can only be achieved by ideal gases. Now friends, what is ideal gas? The ideal gas is a gas which reaches to the absolute zero. That is, all the it reflects to all the temperature, is it is absolute zero or the highest, right? You have to keep all these 4 points in mind. Now see, the ideal gas, we have to understand this. We are not going to details. You just have to understand what is ideal gas equations, right? In higher studies, you'll be using it up. What is the definition? That it is a equation concerning a hypothetical ideal gas. As I have told you, no gas till now has been reaching absolute zero temperature. So it is a very hypothetical gas. And who gave this equation? The equation is given by Amelie Chaperon. He's the scientist. He gave this equation, or you can say ideal gas law, in 1834 as a combination of Boyle's law and Charles' law. So it can be expressed in this manner, where P is a pressure, V is a volume, N is a number of moles, R is the gas constant, and temperature. So what is the value of gas constant? It had been calculated in the laboratory. That is, R is 0.082057 liters atmosphere per mole per Kelvin, or you can also write in another unit, that is 8.3145 joules per mole per Kelvin. So friends, this was the session which we have ended up. Now it's time for the activity. You have to fill the boxes. What boxes? Yes, you have to fill the left out boxes, the Kelvin box and the Fahrenheit box correspondingly. What will be the temperature with respect to 96 degrees centigrade? You have to fill in the 5 minutes. Let's do it in less than 5 minutes. I know you know this. So, what is the second activity? This is a bit of theoretical activity. You have to just correct the statement very fast. First is the boiling point of the water is 273 degree Kelvin. 0 degree centigrade is equal to 0 Kelvin. Standard temperature is 25 degrees centigrade. Ideal gas equation is for hydrogen gas. Ideal gas equation is PVN equal to RT. We can use degree signs in absolute temperature scales. Celsius scale is used as STP. What is ST? That is standard temperature pressure. I know you know this. So friends, I hope you have understand this uh, new session. So in next session, we'll be discussing the how tips of the numericals, how to solve the numericals very easily, because these are the basically very important part of any theory, right? So in next session, we'll be meeting with solving numericals of gas laws. Thanks for today. Thank you, friends. I hope you have understand this.